In this video, we're going to get an introduction to one of the most important concepts in calculus. It's called a limit. And limits build all of our material for calculus. Limits are the basis of everything in Calc 1, 2, and 3. So it's very important to understand exactly what a limit is, even if we end up not using them directly in the future. So we'll start with the definition. We are going to let A be a real number. And we're going to suppose that f of x is a function that is defined near A, but maybe not at A itself. Then we write that this limit as x approaches A of f of x equals L if the values of f of x get arbitrarily close to L as x gets sufficiently close to A. So what this is saying is that a limit is the behavior of a function near a particular value, but it might not actually be the function value evaluated at A. It's just what the function appears to act like near A. It makes more sense when you see a picture of what's going on. So I'm going to draw a couple of examples of what a limit as x approaches A of a function equaling L actually means. So we're going to draw some examples of limit as x approaches A of some function equals some value L, and what this can possibly look like. So if this is the value A over on the x-axis, and I'm just going to say this is L over here, I'm going to draw an example of a function whose limit as x approaches A approaches L. So I'm just going to draw a nice function. It doesn't matter what it looks like. And now we can see from this function, I'm going to call this function f of x, that as I get closer and closer to this value A from both sides, the y value of my function gets closer and closer to L. So we're saying the behavior of the function near A is L. Now, some of you might be wondering, well, it looks like f of A is exactly equal to L, so what's the difference between a limit and evaluating a function? Well, when you have a continuous function like the one I just drew, yes, the limit is going to equal the actual function value. And we're going to talk about that in detail in a few videos from now. But this is not the only case of having the limit equaling L. I'm going to draw another couple examples, just altering this one we have here. Here's a different function. It looks about the same as the function we just had, except it happens to have a hole at A. But as I approach A from both sides, my x values get closer and closer to A. The y values are still getting closer and closer to L. So notice that here I have f of A is undefined because I have a hole in the graph. But the limit as we approach A is still equal to L. it looks like the function should be getting close to L as we get closer to plugging A in, but if we actually plug A in, that value f of A doesn't exist. That's okay. So this is another example of when you can have a limit equaling L. It doesn't have to actually have the function defined at that value. Now let me change this up a little bit more. So we showed how even if f of A is undefined, you can still have a limit as you approach A. And here's another interesting case. Let's just say this value up here is some number n. So on this particular function, f of A is defined now. Right here, f of A is equal to n, but when I approach A from both sides, it looks like my function's behavior is getting closer and closer to L. So you can have your function be defined at a particular point, but still have a different value for your limit. Remember, the limit is not talking about exactly what happens at A, it's talking about what happens as you get close to A. So on this particular function, as we get closer and closer to A from both sides, it still looks like my function should be L at that point, even though it actually isn't. The actual function value is way up here at n, but the limit is talking about the behavior near A and not actually at A itself. So let's do some more concrete examples of limits. We are going to examine the behavior of the function f of x equals x squared minus x plus 2 for values near 2. And we're going to do that to guess what the limit as x approaches 2 of this function, what that actual limit is. So in this problem here, we don't really know how to evaluate a limit yet. We're going to learn more about that in the next video. Right now, we're just trying to think of the intuition. So we're going to be using a lot of graphs, or we're going to just plug in values that are very, very close to 2 and see if we can determine the behavior of the function. So that's what I'm going to do here. I'm going to make a table of points and plug in some values that are very, very close to 2, but not actually equal to 2. So I'm going to try, let's do 1.99 and 1.999. On the other side of 2, I'm going to do 2.001 and 2.01. All of those values are very, very close to 2, but I'm not actually going to plug in 2 to see what this limit is. I'm going to instead evaluate this function at these different values that are close to 2. So you guys know what this would mean. I would have to take this 1.99, plug it in for all of my x's. If you plug that in and most likely use your calculator, you're going to get 3.970100 approximately. When you plug in 1.999, you're going to get 3.999001. And then on the other side of 2, the number is a little bit bigger than 2. When I plug in 2.001, I have 4.003001. And when I plug in 2.01, we have 4.030100. So just looking at these values near 2, we can make a guess for what the limit as we approach 2 is equal to. Notice on one side, I'm getting closer and closer to 4 from numbers slightly smaller than 4. And on the other side, I'm getting closer and closer to 4, but my numbers are slightly bigger than 4. So our guess, looking at this information, our guess is that the limit as x approaches 2 of this particular function is going to be 4. And that is correct. We will talk more about how to actually evaluate the limit rather than guessing by putting values near 2 in there. We'll talk about that in the next video. But for now, we're just trying to get the idea of what a limit is. We're trying to see what does it look like my function should equal at that particular value without actually plugging that particular value in. Let's do another example. All right, for our next example, we're going to look at the behavior of f of x equals x minus 1 over x squared minus 1 near 1 to guess what the limit as x approaches 1 of our function is. Now, before I start actually plugging values in to guess what this limit is, I want you to look at the actual function. Unlike the previous problem, where I could have just plugged the 2 in and gotten the correct limit guess just by doing that, if I plug this 1 into this function, my function is undefined because I'm dividing by 0. So I don't have a function value f of 1. We can't do that to just guess what's going on. So we're going to guess what this limit is by, again, checking values on each side of 1. So I'm going to use 0.99, 0.999, 1.001, and 1.01 to try to guess what this behavior is as I get closer to 1. Now, if you take these values and plug it into this x minus 1 over x squared minus 1, when I plug in 0.99, I'm going to get 0.502513. When I plug in 0.999, we get 0.500250. And then on the other side of 1, plugging in 1.001, we get 0.499750. And plugging in 1.01, we get 0.497512. So looking at this, we can guess that the limit as x approaches 1 of our function is, well, what do you think it actually is? On one side, it looks like we're getting closer and closer to 0.5. On the other side, it also looks like we're getting closer to 0.5. So a very logical guess would be that this limit is equal to 0.5 or 1/2, and it actually is. And in the next video, you'll have the technique for how you can actually evaluate the limit rather than guessing. All right, so now we need to talk about what a one-sided limit is. So far, all we've been doing with our limits is checking what happens on both sides of the number we're approaching to see what the behavior of the function is. But sometimes we're going to have to consider the behavior from one side versus the other side. So that is where one-sided limits come in. So when we approach it from the left, we write that the limit as x approaches a from the left side of f of x equals L. So this little minus sign that I have that looks like an exponent on my A, it's not actually an exponent. It's just notation saying that we're approaching A from the left side, numbers that are a little smaller than A. And when we approach from the right side, we write that limit as x approaches A from the right side of f of x. I'm going to call this one n, because there are cases where the limit from one side does not equal the limit from the other side. So to say that you're coming from the right side, number's a little bit bigger than A, we use a little plus up here that looks like an exponent, but it's not, just notation. So when I'm talking about approaching from the left side, I'm talking about here's my function, here's A. Actually, let me make it a different type of function like this. So coming from the left side, here's L, here's N. To match what this description is, when I come from the left side, that's going to be approaching A only from the left side, and that limit looks like it's going to be L. And coming from the right, I'm going to do that one in green, we just approach from the numbers that are a little bit bigger than A. And you can see that one is getting closer and closer to N. So sometimes your one-sided limits are not equal to each other, and sometimes they are. And we will, actually, the very next theorem says what it means for the limit to actually exist in terms of these one-sided limits. So a theorem for us. The limit as x approaches A of our function equals L if and only if the limit as x approaches A from the left equals L, and the limit as x approaches A from the right is also L. So this is just saying that in order for a limit to exist at a point, the left and the right side limits must agree with each other. If they don't agree, we say that the limit does not exist. So let's do an example where I'm going to draw a pretty complicated graph, and we're going to try to find a lot of different limits. Some from the right, some from the left, some in general, and see if we can figure them out by looking at the graph. Let's get this graph up here. It's going to be kind of a strange looking function. We're going to have a point up here at 0, 3, another point at 1, 2, a hole up here at 2, 5, a point at 2, 1, a hole at 5, 4, and a point at 5, 2. And now let me draw the rest of the function in here. So there's the graph of our function. I'm going to call it G. And we're going to try to find a lot of different limits based on just this graph. The first thing we're going to try to find is the limit as we approach 2 from just the left side. So what is the limit as we approach 2 from only the left side of this particular function? So that means I need to find where x is equal to 2, and I'm only going to follow my function from the left side, so numbers a little bit smaller than 2. So I'm walking along my function here, and what does it look like the y value of my function should be when I approach 2 from the left side only? Well, that looks like I should have a y value of 5 way up there at that pole. So the limit as we approach 2 from the left of this function is 5. It looks like when we're approaching only from the left side that the behavior of the function is getting closer and closer to 5. Part B, let's find the limit as x approaches 2 from the right side only. So we're going to do a similar concept here, except instead of approaching from the left, we're going to approach only from the right. So I need numbers bigger than 2, and I'm going to follow my function, get closer and closer to 2 from the right side only. What's the behavior of the function as I get closer to 2? Well, it looks like I should be getting 1. So the limit as I approach 2 from the right side is equal to 1. Now for part C, we want to find the limit as we approach 2 from both sides of our function. Well, we've already done all the work for this. We've looked from the left and we've looked from the right. That theorem we had just written down said that the limit as we approach 2 will only exist if the limit from the left and the limit from the right equal each other. Well, I got 5 from the left and 1 from the right. So they're not equal, and that means that the limit in general does not exist. Because if I approach 2 from both sides, I get conflicting information. I can't determine the behavior of the function near 2, because going from the left and right, I get different results. Now, part D, instead of talking about a limit, what is g of 2 equal to? So g of 2 is asking us what's the y value when my x value is equal to 2. That's going to be this point right here, not the hole up top. And this point has a y coordinate of 1. So notice that in this case, we have a left-sided limit, a right-sided limit, and an actual function value at 2, but we don't have an actual limit as we approach 2 because my left and right sides don't agree. So this is one of those cases where our function is defined at the value, yet my limit does not exist. They don't always agree with each other. The actual function value is talking about what happens when you plug this value into your function, and the limit is talking about what happens to your function as you get close to this value, but maybe not actually at that value. All right, we still have more to do on this example. We've talked all about what happens near 2 and at 2. Now we're going to do the same thing for 5. So part E, what is the limit as x approaches 5 from the right side of my function? So remember, I already said it out loud, but that little plus there means we're coming from the right side. Here's where x is equal to 5. I want numbers on the right side of it. So I'm going to follow my function as I get closer and closer to 5, but only from the right side. Let me erase all of our work from 2 just so we don't confuse ourselves. So as I get closer and closer to 5 from the right side, it looks like the y value of my function is getting closer and closer to 4. So the limit as I approach 5 from the right is equal to 4. Now let's try the same thing, but from the left side. To find the limit as we approach 5 from the left side, I need to look at numbers that are a little smaller than 5. So I'm coming from this left side, seeing what happens as I get closer and closer to 5 from this left side. And it looks like the behavior of the function is saying we should be approaching the y value of 4 again. So both the left and the right side limits gave us 4. It looks like the function's getting closer and closer to 4 as my values are getting closer and closer to 5. Part C, what is the limit as x approaches 5 of my function in general? Well, remember that our theorem says that the limit as we approach A equals L if the left and the right-sided limits as we approach A are both equal to L. So in this case, the limit as we approached 5 from the right and from the left, we got an answer of 4 both times. They agree with each other. That means my overall limit, both the two-sided limit exists, and it is also equal to 4 because it matches the agreement between the left and right-sided limits. And just to finish up this problem, and I called that C instead of G, and this one's going to be H. G of 5. G of 5 is not talking about the behavior near x equals 5, but the actual function value when I plug 5 in. So when I look at my graph here, x is equal to 5 right here, and where I actually have a point on my graph is this point right here, not the hole up top. And this point has a y value of 2. So my actual function value at 5 is equal to 2 because that's where the point is. But the limit of my function as I approach 5 is equal to 4 because as I get closer and closer to 5 on both sides, my y value looks like it's going to be 4, but the actual function has that y value of 2. So this shows how you could have one-sided limits not agreeing with each other. You could have the limit actually existing with the one-sided limits agreeing. And you can have the function value not equal your limit even when the limit exists. There's a lot of complicated things that can happen with limits. So in our next video, rather than just figuring out limits by plugging in values close to the value we're approaching, or by looking at a graph and drawing arrows showing which way we're coming from, we're going to actually learn some algebraic techniques for how to evaluate the limit. So stay tuned, and if you have any questions on this particular video, feel free to drop them below. If you're one of my current students, you can also ask your questions through email or in office hours. And I'll see you next time for computing limits algebraically.